Hi, everyone. Welcome to the Third Coast Water Seminar. This is our first of 2022, and we are really excited to welcome you all to hear from a wonderful speaker on a very important topic, integrating systems for potable reuse and desalination. My name is Elena Harkness, and I'm the Executive Director of Current, and I'm very proud to be the host of the Third Coast Water Seminar Series, along with our wonderful co-hosts, Northwestern University, the University of Illinois Urbana-Champaign, Argonne National Laboratory, the University of Chicago, and the University of Illinois at Chicago. Together, these institutions represent the collective heavyweight power of so many different disciplines that focus on different aspects of innovative water research and technologies. And all of us have come together under the Third Coast Water Seminar banner to bring you a new speaker every month, sharing new perspectives on advances in water research that are applicable here in our backyard in the Third Coast in Chicago, but also all around the world. So really excited to welcome you today. If this is your first Third Coast, just a few logistics. We love to have Q&A from our audience, and we also love to see general comments in the chat tab, so feel free to use both of those liberally. This event, like all of our Third Coast Water Seminars, is recorded, and the link will be shared on our event page and Current's YouTube channel. So subscribe to that if you don't already. There's terrific past event recordings up there for your viewing pleasure. And you'll also get the link if you registered for this event to share out after it's over. We have a very simple agenda format here at Third Coast. I will be introducing one of our co-hosts, Junhong Chen, the lead water strategist and senior scientist from Argonne National Laboratory, and the Crown Family Professor at the Pritzker School of Molecular Engineering at the University of Chicago. Junhong is one of the original brains behind the Third Coast Water Seminar, and he's going to introduce our speaker today, Dr. Amy Childress from the University of Southern California. We'll have about 40 minutes of presentation and then 10 minutes for your Q&A, and then wrap you up just before the top of the hour. So just a bit of background on Current and why we're here. Current is Chicago's water innovation hub, and we're a young organization who collaborates to grow our inclusive blue economy, help accelerate innovation, and solve persistent water challenges. Why are we here? Well, Current exists because we believe, as we know so many of you do, that we need much more healthy water for all of us to drink, and here in our region particularly, less flood water for our basements. That's our shorthand for dealing with the effects of climate change on our water supply and on the water that we experience in our environment. But we also believe we need more blue jobs that are putting people to work in the water industry and companies that are solving water challenges all around the world, driving innovation. Our problem statement is that this innovation could happen faster if we had collaboration. So we really strive to build the kinds of interdisciplinary and cross-sector partnerships that help advance water technology faster, bring it to market, bring it to scale, and help de-risk novel solutions to help make sure we get them into market at the scale that we need to address these issues. Current does this by striving to be an unbiased advocate for water policies and solutions. It's not always technology, but often involves technology. So we try to stay on top of the field, understanding what's new, what's different, and how it applies to different markets and in different conditions. We do independent assessment and validation of technologies, and we often recommend solutions for others to try or for us to pilot with partners. But we're more than a connector, and we often test new technologies and ideas in the real world. On the right, you see one of our interns working on our real-time water quality monitoring here in Chicago in the Chicago River, the first of its kind platform for testing microbial water quality in an urban river system. And we're really excited to have that out in the field for its second recreational season here in 2022. And we're constantly building a pipeline of new technologies to help meet emerging challenges, like sewage surveillance. We're part of a multidisciplinary and multi-institutional team using wastewater as an early warning and detector for SARS-CoV-2 and other public health indicators. Nutrient management, we are looking at how to mitigate the contamination from excess nitrogen and phosphorus in Illinois waterways, thinking about how to capture and utilize wastewater energy as a renewable source, and figuring out how to target and destroy PFAS and other forever chemicals, a persistent threat to our water quality here in the region. And at the forefront of all of this is a strategy for our region to help grow an inclusive blue economy where everyone has the opportunity to get excited and inspired by these novel innovations in water, the challenges that are all around us and changing all the time, and can see an opportunity for education, employment, wealth building, and overall advancement in this industry. So to that end, we have an array of programs that are focused on that overall strategy, on blue jobs, on educational opportunities, and on the leadership that our corporate community needs to have in order to be effective and inclusive water stewards. So that's current. And now, again, to demonstrate the power of the partnerships that have brought Third Coast to life, I want to turn it over to one of our co-founders, Junhong Chen from UChicago and Argonne National Lab, to introduce our speaker. Junhong?
Thank you, Elena. Good afternoon, everyone. It's my great pleasure to introduce our speaker today. Dr. Amy Childress is Gabelling Distinguished Professor of Science and Engineering and Director of Environmental Engineering at the University of Southern California. Her research team seeks holistic and realistic solutions to the problem of finite water and energy resources. Some of her projects include pressure-driven membrane processes as industry standards for desalination and wastewater reclamation, membrane bioreactor technology, and colloidal and interfacial aspects of physical-chemical processes. Dr. Childress has received many awards for her publications, research innovation, technology, education, and mentoring. She chairs and serves on expert advisory panels on potable reuse and desalination. She's also a co-editor of the journal Desalination and serves on the US EPA Science Advisory Board. So without further ado, please join me in welcoming Dr. Childress.
Hello. Thank you for having me. Let me share my screen. Oops, okay, wait. Here we go. All right, thank you for the introduction, Junhong. That was very nice. I'm going to jump in because I do have at least 40 minutes of presentation, so I'll get started. It's a pleasure to be here for the Third Coast Water Seminar Series. I thought I would start my presentation with a fact check because I've heard of a reference to the Third Coast before, but I'd never really thought about it. So I did look up coast to see if it is the part of the land near the sea or the ocean as I was thinking, but they also had a definition, the edge of the land, which I guess could apply here. And I did also in my Googling find a chart of size and salinity of lakes and oceans. And the reason I found it interesting is because it shows the global ocean and Lake Michigan kind of close together. And I thought, wow, who knew? But that's in large part due to the very saline lakes they consider, which stretches out the scale, and also due to a huge break in the scale on area. But going forward with our work today, we consider the ocean salinity a global value of being about 34,000 milligrams per liter. I looked up the Lake Michigan salinity and found that it's about 15 milligrams per liter. And this was a very recent article that from January 8th that shows the salinity in Michigan has increased from 1 to 2 to 15 milligrams per liter. I'm going to grab a pointer really fast. Let me see. I'll just go with red. Are you seeing my pointer real quick? Anybody? Okay, I'll assume you are. Okay, so a big difference between these two salinities, but of course, this increase in salinity is a concern for Lake Michigan because it puts wildlife at risk or just might change the ecosystem. After a little more Googling though, I found that perhaps the greatest risk right now could be the slogan unsalted and shark-free might not be so valid. So, but the takeaway here is that salinity is important in lots of regions across the US and around the world, and that values of salinity must be considered relative to the systems we're measuring them in. So the other thing I like to do in my free time is look at the US Drought Monitor. And this shows the most recent Drought Monitor map. So I was kind of looking in this Third Coast region. which does have areas of dryness and areas of drought. And if we look back, this is 2017, perhaps even greater dryness and drought. I know the concern more recently has been flooded basements, but you can see in the recent past that dryness and drought are also a concern. And going back to 2013, you can see even more drought, almost on the scale of the second coast. So the second coast is what I'll be talking about today. And we'll start with some coastal California water supply portfolios. So to address this drought situation and address the changing water supplies, a lot of the water agencies develop water supply portfolios. This one comes from West Basin Municipal Water District. It's a little bit older portfolio, but it was projected for 2030. You can see a good chunk here. Good portion comes from importing water from the Colorado River or from Northern California. There's another good portion that's local groundwater. And conservation. So conservation is also shown as a water supply. And then there's also a part that's non-potable or recycled water, and a potential desalination, ocean desalination project that's been in the works for about 2 decades that, as of last month, was terminated. And so this was kind of a big deal because, like I said, it was a project that's been in the works for 2 decades. If we look at a second water supply portfolio, so this is San Diego, you can see a good portion is attributed to conservation. And then you see another significant portion to potable reuse, a smaller portion to seawater desalination, and then I'll point out also the recycled water. So, oops, let's see, what did I do here? In the US, there's kind of been this staging of water reuse versus seawater desalination and which one will win. There's a lot of public opinion involved in it, and that public opinion does have political implications because water districts are overseen by boards with elected directors. So public opinion translates to decisions in some cases. There's also regulatory hurdles both for water reuse and for seawater desalination, significant ones. On the California coast, you might expect seawater desalination would have won out. But in fact, if you consider that the highest populations are along the coast, that means there's a lot of wastewater available. So it hasn't won out. The general consensus has been to do both. So we have our surface and groundwater sources that we still would rely on, imported water as well, but we would bring in potable reuse and desalination. And you see, I show desalination here as a smaller piece, and that's because it typically is the most expensive water supply option. So we'd like to use as little of it as possible, but I also show it in the base. And that may seem counterintuitive if it's the most expensive water supply option. But for water agencies, it's easier to justify the investment in this facility if it's going to be in constant use and be a part of the base load. So I'm going to show it here, but we're going to talk about that again later in the presentation. So a very quick review of reverse osmosis. In reverse osmosis, you have a feed stream, a pressurized feed stream entering a membrane module. The blue dots are water. We'll call the orange dots salt, because in this case, we're trying to remove salt. The permeate, the relatively clean permeate, is what passes through the membrane, and you're left with a concentrate or brine that has to be disposed of. The variables here, flow rates, pressure, and concentration. A lot of times we're interested in the rejection of the membrane, what remains in the permeate or what was rejected by the membrane. And we're also interested in the recovery. How much of this original feed did we recover as permeate? So we'll go to a coastal water system, and I'll talk about how those reverse osmosis membranes are used. So if we have a city that has part of its water supply coming from the sea or the ocean, I should say it is the ocean, but seawater desalination is a term that's more recognized. So a lot of times, even though we're talking about the ocean, I will be referring to seawater desalination. So here we have the ocean water coming in to the seawater RO membrane, drinking water coming out, a brine being returned to the ocean. You could approximate this, and we will be at about 50% recovery. So 50% of the water that comes in is drinking water, 50% is returned as a high salinity brine. On the other side of the city, we have the wastewater coming out, going to a wastewater treatment facility that historically would discharge back to the ocean. But now we do some tertiary treatment and use that water, use some portion of that water for non-potable reuse. And it's becoming a little more common to perhaps send another portion of the water to an advanced water purification facility for potable reuse. And in California in particular, this is often done with RO membranes. I'll call these wastewater RO membranes. It's just maybe a little bit shorthand to do that. So that's what we're interested in, the potable reuse with these wastewater RO membranes. So briefly, if I tell you about the seawater desalination challenges, I would start with energy consumption. Seawater is one of the most energy intensive. It is the most energy intensive water supply. Of course, if you're comparing to pumping water from Northern California over the Tehachapi mountain range, maybe the energies are coming close. So energy consumption is a major concern. Also, on the intake system, impingement and entrainment of marine organisms on the uptake screens or in the intake system is an issue, and it's led California to suggest using subsurface intakes when feasible. The question becomes, if the subsurface intakes double the construction costs and the construction time, is that still feasible? That's up in the air. Lots of good questions around that. And then we also have the concern with brine discharge, where the brine, because it's dense, sinks and spreads along the ocean floor, where it affects benthic and other organisms. We try to mitigate that with diffusers and dilution. The brine discharge issue is unique to seawater desalination facilities because of that density, whereas seawater intake issues apply to power plants and other facilities along the coast. So in the past, we've co-located desalination facilities next to power plants. And a lot of people think that we've done that because desalination facilities need a lot of electricity and power plants can supply it. And it is true that on-site electricity rates can be cheaper than transmission rates. But the real reason for this co-location is probably more related to the intake and outfall infrastructure and the water within that infrastructure. And the permitting of that infrastructure is perhaps most important. And so the desalination facilities can share that water, and that has made the co-location nice. But as many of you probably know, these once-through cooling systems are being phased out. And so now there's interest in co-locating near the wastewater treatment facilities. And the reason is, if we blend the treated wastewater that we're already discharging to the ocean with the high salinity brine, we can dilute that brine to meet regulations and have a viable desalination facility. So this is a co-discharge scenario, and it currently does happen in some locations. And this is where our work kind of took off from here, which is, can we do more than mix these waste streams for discharge? Because if you think about it, the water resource that's in this treated wastewater is being lost to the ocean. And we asked the question, how can seawater desalination and wastewater reuse operate synergistically to optimize both water and energy? So we developed a framework, and the framework, I'll show it to you in a minute. It's a simple framework. Its value is in by putting together the pieces of these systems, we could analyze them and think about the feasibility of these ideas that we're considering. So we developed a framework, and in the first part, we took a seawater, it wasn't that we took it, we just came into the project with a seawater desalination perspective. What's the best blending scenario to meet a discharge regulation of 40 grams per liter? And discharge regulations aren't always that simple. 40 grams per liter, really it's different concentrations at different distances from the discharge point, but we just simplified to 40 grams per liter for this study. We also wanted to make the best use of the treated wastewater still. So these are the two scenarios we considered. We considered that, well, actually considered more scenarios, but these are the two I'm going to show you. We considered this co-discharge scenario or brine blending. So this is the what is currently being done in some locations against a potable reuse scenario. So feed blending or a proposed future scenario. So I guess what I want to emphasize here, this is not being done. This is something we're saying could be done in the future, and of course would be subject to potable reuse regulations. So what we're doing here is bringing the treated wastewater in on the feed side. So we would treat the wastewater with advanced processes and then blend it with the intake seawater. The advantage being the RO membrane would see less osmotic pressure, so we have less pumping, less energy costs, and at the same time, our discharge would be at a lower concentration. So we thought there could be some interest here. This is the framework we used. This is the secondary effluent coming in and being blended. The seawater intake going through ultrafiltration. We modeled using wave design software and power model for the energy recovery. We used pressure exchangers for all scenarios, and we used wave also for the seawater RO. So for the UF, we assumed a recovery of 90%. For the seawater RO, a recovery of 50%. And we're blending the waste streams from these processes. The permeate stream goes on to the water distribution system. This is the framework for the potable reuse scenario. What you see is the blending happens upstream of the reverse osmosis now. And we also implemented UV AOP after the RO for those low molecular weight organics and other things that can pass through an RO membrane and that we find in wastewaters. We used a wastewater RO recovery rate of 80% for the treated wastewater. And we took an overall, when we blended the streams, so the seawater where we used a 50% recovery rate and the wastewater 80%, we just took a weighted average of the two. And we applied the framework to the Charles Meyer desalination facility in Santa Barbara, California. So this is a medium-sized desalination facility. I'm going to go with 3 MGD. It helps keep the numbers easier. So it's a 3 MGD facility located less than 0.1 mile from the El Estero wastewater treatment facility, which treats with secondary treatment using activated sludge, and it's an 8 MGD facility. So half of that 8 MGD is tertiary treated, filtered, and it goes on to non-potable reuse, golf course watering or green space watering. The other 50% or almost 50% is blended with the seawater RO concentrate and discharge 1.5 miles into the ocean. So this is that co-discharge option that I mentioned. So I'm going to show you some results of our blending. And the way I'm going to show it to you is in the form of always as a function of the seawater to treated wastewater ratio. So if we look at the RO influent flow rate as a function of seawater to wastewater influent ratio, and we consider the 100% seawater. So this bar on the left represents 100%. Actually, I'm just going to ask real quick, can you see my pointer?
We can.
Okay, good.
Yep.
Okay. I didn't want to get into the graphs without knowing that. Good. Okay. So the 100% seawater option, and if we consider that we are operating seawater RO at 50% recovery, what this bar represents is how much water gets treated by the reverse osmosis to achieve 3 mgd product water. On the other hand, if we're looking only at treated wastewater, so this is the fully potable reuse scenario, if we're assuming 80% recovery, then we need much less water to achieve 3 mgd. And then we see the blends in between. So a 60% seawater, 40% wastewater blend is shown here. What you can easily see from the graph is that as we go to greater wastewater in the mix, less water needs to be desalinated. And also what that translates to is less seawater intake infrastructure. So there's environmental consequences with that, and or environmental benefits of that, and economic benefits as well. And this is kind of obvious, right? Wastewater recovery or wastewater reclamation is typically thought of as being cheaper and better than seawater RO. So nothing so great here, but again, we put it into this framework of thinking. Next, we looked at the treated wastewater that's required and how it's used. So the treated wastewater flow rate, either used for discharge dilution, so just a picture here, discharge dilution, or for influent dilution. So the discharge dilution represents this 100% seawater case, and the bars that are only light purple are this influent dilution case. And then we have some of these bars in the middle that have both discharge dilution and influent dilution. So I'm going to bring in an arrow down here to represent that as well. Now, if we're trying to make the greatest use of the water resource, we would prefer to only have influent dilution and no discharge dilution, right? And if so that would tell us that operating with 40% seawater, 60% wastewater, we could make seawater RO viable and also makes the greatest use of that water resource. We ask, do we have enough treated wastewater to do that? And in fact, we do. So again, the seawater desalination perspective. We looked at discharge flow rates and components. So what's being discharged? And again, if we go to this 40-60, that's where we drop off this dark purple or treated wastewater that we would be wasting to the ocean. And we can see that the rest of the components are UF retentate from the treated wastewater, RO brine, and UF retentate from treating the seawater. A key takeaway from the graph is, again, as we have more wastewater in the mix, there's less discharge to the ocean. Another thing we looked at was the reduction of boron concentration from blending. So boron is present in seawater at 4 to 6 milligrams per liter. We often use 2-pass RO. So we take the permeate from a first pass RO and send that, we actually raise the pH and then send it through a second pass RO to bring boron to regulatory levels. So here we're looking at the boron concentration in the first pass RO permeate, still as a function of our ratio. And if we bring in the California state notification level for boron, it would be here. So what we see is if we operate at a 60-40 ratio, we can be under that California state notification level only with the blending. We don't need the second pass RO. And if we looked at the RO-specific energy consumption, which we were all along, but I'm just showing you the data now. Here we're looking at energy from the first pass RO and energy from the second pass RO. By no longer needing the second pass RO, you can see a significant energy savings by avoiding it. So some benefits, some chemical benefits, or benefits to the chemical species, I guess. This is a summary for these two conditions that I've been talking about, the brine blending scenario and the 40-60 blend. Flow rates on this side and specific energy consumption on the other side. So the key advantages, if we look at how much seawater and infrastructure is needed in our current scenario versus what we're proposing, that's a significant decrease. And if we look at the purple bar is treated wastewater, not much change there. If we look at the gray bar in terms of what's discharged to the ocean, we see a significant decrease with our potable reuse scenario. And if we look at net SEC, we also see a significant decrease with this potable reuse scenario. But we said, we kind of stepped back and realized that how we started this work, focusing on this seawater desalination, was no longer where we were at. We were realizing we need to be just looking at both systems and thinking, what's the best thing to do here? And the best thing is to maximize the use of treated wastewater that's available. So what the results told us is we want to move the potable reuse down into that base load and bump desal up a little bit. So if we go back, this is the data you've already seen on the treated wastewater flow rate, and this is how much wastewater is available. If we come in from this perspective of using all the treated wastewater available, this is what we'll call integrated facility perspective, we might choose to operate up here. And really this was kind of where the project, there was a paradigm shift. We realized we were approaching this with a wastewater, from a wastewater augmented seawater desalination perspective to a seawater augmented potable reuse perspective. And we are continuing along this seawater augmented potable reuse path because we think it's interesting. Again, it's a thought experiment. It's nothing that's being done. But I'll tell you in the next slide why we think it's interesting. When I went over the seawater desalination challenges, I might have kind of skipped one of the most important ones, which is demand risk. That's if less expensive water supply options become available, the demand for the water from seawater desalination decreases. And this could have played a key role in West Basin deciding not to go forward with a seawater desalination facility, because demand risk has caused the original Santa Barbara facility, the Yuma desalination facility, it's agricultural desalination, and several facilities on the east coast of Australia to be mothballed. So this was back, these facilities were built in response to a drought in the late 80s. They were never even used at full capacity for a whole day before being mothballed. So demand risk is a scary thing, which means the ideal thing would be to move that desal block up to the top in some sort of peaker roll. But that goes against the water districts who don't want to think of desalination as a peaker roll because you have all that infrastructure. But we think if a concept of seawater augmented potable reuse was available, there could be an opportunity. So I hope I demonstrated the multiple benefits of the potable reuse scenario. Potable reuse scenarios. Sorry. I blame all mistakes on COVID. Okay, so multiple scenarios, multiple benefits, including energy, cost, and footprint savings. our goal was to make the highest use of the water resource embedded in the treated wastewater. We are moving forward with how can we protect seawater desalination from demand risk. And the second project I'm going to show you today ties into this last question. Is there enough wastewater available to meet potable reuse demand? Are other sources available? So study number 2, the setup is a little bit different. So here we've got the wastewater influent, a wastewater reclamation facility going to the advanced water purification facility that you've already seen. But this is a wastewater treatment facility now that we're including in here. And the first thing I want to point out is that salinity in our wastewater is increasing. It's due to residential water treatment systems, water conservation measures, industry. There's several reasons. Also in coastal areas, it's due to seawater inflow and infiltration, basically due to aging infrastructure and leaky gates and perhaps some corrosion, that seawater can pass into the pipes that feed the wastewater reclamation facility. And that would also increase salinity. And all of this is exacerbated by climate change. So, and all of this, because salinity is conservative, it passes through the wastewater reclamation facility and is only treated once it gets to this wastewater RO in the advanced water purification facility. So maybe you have to operate that RO at higher pressures. But we said if existing RO systems can already accommodate this additional salinity, can we use these RO systems to treat higher salinity streams that we currently consider waste streams? So one example of this involves what's called a regional brine interceptor collector. Inland from the coast, we have brackish water RO systems and waste agencies that like to discharge either the brines from their desaltered or their concentrated waste streams into this interceptor or collector. And right now what happens is it comes into the wastewater treatment facility separate and is discharged to the ocean. It does not go to the advanced water purification facility. An example of this is Orange County Water District's groundwater replenishment system that is currently undergoing expansion from 100 to 130 MGD. And they have a regional interceptor collector that's discharged to the ocean. Could a portion of the flow in that regional brine interceptor contribute to the additional influent needed? And that was our question. The second scenario is we also have out there in inland regions, brackish water reverse osmosis brines. And these brines can go up to salinities of 10 grams per liter, which is considered high in the brackish water world. Of course, compared to seawater, it's 34 grams per liter, so it's not so high, but and relatively low TOCs because they've already been pre-treated. So we asked, can these brines be brought in either upstream of the wastewater reclamation facility or downstream of it? And right now, this is being done. This is not brand new. This is being done in some locations, but a lot of other locations are discharging their brine to disposal wells or evaporation ponds and not making use of that water resource. So we asked if we can recover these flows by blending. So we're going to bring down that salinity by blending with the wastewater and desalinating. What are the energy implications? And then with both of these together, I have to throw out the big question that we kind of started with. Can these high salinity streams, we call them high salinity, they're only higher than the existing wastewater. They're not higher than seawater, you know. Can these streams be treated at no additional energy cost using devices or processes that are typically not implemented at advanced water purification facilities? All right, these were our objectives. We're weighing the water supply, the additional water supply against the energy consumption. We're looking at using energy recovery devices or high recovery RO. We considered inorganic scaling that could occur. And we also considered permeate and brine discharge salinities within the context of local regulations. The systems we considered, first a two-stage RO system, and in this system, the brine or concentrate from this first stage is sent to the second stage. And this reduces the energy consumption by decreasing the irreversible work or the energy that's lost in the desalination process. So we're already considering energy just with the two-stage RO. We looked at a second scenario, bringing in an energy recovery device. Now, you have to take seawater desalination out of your mind here, because at seawater desalination facilities, energy recovery devices are standard, but they are not standard at brackish water RO or wastewater RO potable reuse facilities. So we said, can we bring this in? And what they do is transfer the energy that's left in the RO concentrate back to the feed stream. So you need less feed pressures. And the third thing we considered was high recovery RO. We specifically considered the CCRO process because a Dow wave model already existed for that. But we could generalize this to high recovery RO. This is a semi-batch process where the feed comes in, you're constantly producing permeate, and you're recycling the concentrate stream back. And periodically you're doing a blowdown. That's what I'm calling it. That's not the official term, but you're blowing down that concentrate stream. And also there, the goal is to reduce energy consumption because you can decrease the irreversible work by operating with a time variant feed pressure. So all of these were modeled using Dow wave design software, all of them with the intention of decreasing that energy. This was the framework we used. It was for a facility similar to Orange County Water District, a large advanced water purification facility, and that was treating 134 MGD of secondary treated wastewater. So we have the wastewater coming in, intruded seawater. We brought it in at 0%, 2.5, 5, 7.5, and 10%. The 2.5 is probably most realistic, but we also didn't consider just the concentration of the wastewater increasing from reasons other than intruded seawater. So we figured this just kind of represents increasing salinity due to a variety of things. We considered several higher salinity streams, ones that are representative of brackish water RO concentrate. So 5.7, 7.5, 10.9, and 7.5 grams per liter. We had the combined stream going into our advanced water purification facility, and we kept an eye on the salinity of the product water leaving that facility and of the brine that has to be discharged from the facility. And this was the first set of results. Here we're simply looking at the effects of seawater I&I and higher salinity streams on SEC net. So this is SEC net as a function of 0%, 2.5, 5, and so on, seawater I&I. We have a base case for each, which means no additional higher salinity streams were added. And the base case is also indicated by this red line. I'll also point out these black dots are the influent salinity in grams per liter. So we can see the influent salinity increases. And as the influent salinity increases, the SEC net increases as well. A key feature that we found interesting was if we look at what happens at 0% seawater I&I when we add the highest salinity brackish water RO brine, we get a 69% increase in SEC. Whereas at 10% seawater I&I, when that background seawater concentration, or sorry, when that background salinity level increases, we get only a 34% increase in energy required with brackish water brine 3. So we say the rate of increase of SCC net decreases as seawater inflow and infiltration increases. We then looked at using an energy recovery device. So what if these facilities that don't typically have energy recovery devices were to implement one? And so the difference in the bars. So the left bar was what you saw on the previous page. Now we're bringing in the right-hand bar, which represents the SEC net for when you're using an ERD, an energy recovery device. So this difference between the two bars represents our energy savings. And also, if we look at if the second bar is above the base case line, we would say, okay, the ERD can partially compensate for the additional energy required to desalinate the higher salinity streams. But in the cases where the second bar is below the red line, that indicates the ERD fully compensates additional energy required. So simply by installing an ERD, you get some free desalination or energy-free desalination. We thought that was valuable. This is the SEC net when using the high recovery RO. So you're looking, the left-hand bars are all the same. It's just the right-hand bars that have changed. Now you can see the energy savings when implementing a high recovery RO process like CCRO. And we can look at the cases where we only get partial compensation, but we can look at all the cases where the second bar is beneath that red line, which indicates that additional salinity is fully compensated for. This graph shows a comparison of those two. Okay, I just looked at the time, I'm gonna get there. And what you can see just by comparing, so this is RO alone, the green is RO ERD, and the squares are CCRO. We see that there's more benefit to the CCRO process. Of course, you may have higher CapEx and OpEx and concern for control of the variable flow rates that are necessary, which are significant concerns, but there are also energetic benefits. For those thermodynamicists out there who are asking the question, what about just treating the higher salinity streams separately to avoid the entropy increase? That's a great question. We considered it. We looked at treating the higher salinity streams separately. I'm not showing the graph because the differences are very minor. But we went into this with the assumption that agencies that are choosing to discharge to interceptors are doing that because they'd rather pay a fee than carry out on-site treatment. But when we did look, we saw that desalinating the stream separately can reduce the energy consumed, but only slightly. And that separate desalination is more desirable when the salinity difference is greater, as you would expect if you're considering the entropy. But compared, we also looked at the scaling, and by blending those higher scaling streams, or those streams that had higher likelihood of scaling with the treated wastewater, we were able to dilute a lot of those scaling material, a lot of the salts. And so that was a significant savings. So we still think the blended treatment may be the better way to go. Also very important, we did not consider the capital costs and the complexities associated with separate treatment, but we think those would play an important role again in the agency decision-making. The last thing we looked at were the permeate and the permeate salinities compared to the limits. So we took an example limit of 580 milligrams per liter, and we were well within that at a water recovery of 75%. At the higher water recovery, we did exceed that permeate salinity limit. Same with discharge salinity limits at the higher recoveries, the higher recovery and the higher salinity streams, we did exceed that. So in those cases, maybe you need less flow rate of those higher salinity streams, or you'd have to operate at lower recoveries in order to meet your permits. So conclusions, the rate of energy consumption increased caused by the higher salinity streams decreases as that background salinity increases. And if we keep this in mind with expecting the salinity, especially with climate change, as I mentioned, to continue increasing, this has implications for the value of utilizing the water resource in these higher salinity streams. We found the higher salinity streams provide additional influent. It's undergone pre-treatment and has lower levels of organics and other constituents. It does have more ions that are likely to form scale. It's important to have flexibility in where these higher salinity streams are blended, depending on your wastewater, your biological treatment process, and depending on the water quality of the higher salinity streams. And we found that there were cases where we can get desalination of additional salinity at no additional energy cost. That's a free desalination. The disclaimer, this is an important one. Addition of higher salinity streams must be considered within the context of enhanced source control, maybe source separation, and also the capital and operating costs. So we developed a framework. We looked at some current scenarios, future scenarios. In the near term, we proposed minor to moderate retrofits for these potable reuse facilities, and perhaps the treatment of saline streams that are now considered waste streams. In the long term, we're thinking of an integrated facility perspective that helps address energy and environmental concerns. This was the work, the PhD work of Xin Wei, and you can find all of these graphs and more in these two papers. I want to acknowledge my co-authors, Kelly Sanders at USC, and Andrea Achille and Zach Binger at University of Arizona. Our funding agencies, we started with an EPRI grant, and we've also had some fellowships from USC, and great thanks to these individuals for talking to me about these bigger picture things. And last, I leave this for you. Go easy on the salt.
Thanks so much for a great talk, Amy. I guess actually I was going to start with my wrap-up question. I think I'm going to move to the top because go easy on the salt relates to a question that someone had about the source of the saltier Lake Michigan. You very kindly started with a Great Lakes focused frame for this desalination question. So can you talk a little bit about the sources of increasing salinity? Because it's, as I understand, it's not actually due to our wastewater treatment facilities, but something else.
Right. I think my understanding, and this is from a quick look, is road salting, especially in the winter months. And I know that there's been some options proposed to decrease that. I haven't looked any more to know if there's other reasons for the increased salinity.
Yeah, we've understood that as well. And our Metropolitan Water Reclamation District here puts out PSAs about, individuals not putting too much salt on their sidewalks and, their porches and steps and that kind of thing. So it is something to be really mindful of here, especially when we're in these deep freeze moments like we are in Chicago right now. So really great framing to start. So I'd love to hear a little bit more about the regulatory changes that would be needed if we're going to have to, to make some of these shifts and move towards more efficient systems. And in particular, I'm wondering if the rising awareness of the need for climate strategies and decarbonization and net zero plans for cities and municipalities could be a helpful driver, but what are some of the other regulatory dimensions to be thinking about?
Well, I mean, so if anybody, if there are consultants watching this, they're like, this is impossible. You've taken, the very challenging water reuse regulatory framework and added it to the perhaps more challenging seawater desalination framework. I took a little bit of suspension of disbelief and rose above those regulatory frameworks to say, if we are looking at one water, we're not looking at a water's history to identify it, we're looking at a water quality, then let's step back, let's look at water quality, let's think kind of outside the box. So I did take it outside of the regulatory frameworks. I don't, in California, where a direct potable reuse framework is in process, likely this would have to fall under a framework like that, because usually in regions where we're doing seawater desalination, it's because we don't have a groundwater reservoir or the ability to store water. So I don't know if I answered the question.
Yeah, I mean, I think the summary is that it's complicated, but I think you've said, what a lot of us here feel, that one water framework is where we need to go to be able to, meet the needs of the climate future we have. Couple of questions that relate to the brine and what you can recover from it. So, is there a possibility to recover elements like lithium, other rare earth minerals that might both be able to help us offset the cost, but also just, recover valuable material from the brine?
Yeah, definitely. And so our objective, we were looking more at recovering as much water from the brine as possible, but that benefits anything you're trying to do in the brine stream, because you're getting the water out of the way so you can get to those small concentrations of other constituents that you're interested in. So this is moving in that ZLD direction that makes recovering materials from brine more realistic.
Mm-hmm. Great. And then, so a question about the removal of trace organics, like this increasing focus on PFAS from streams, does that affect the calculus of the cost between wastewater and seawater as a source?
Yes, but I don't know specifically how much, but there, okay, so it could help things, because if my understanding is that RO membranes are good at removing PFAS compounds. So before I say this, though, I don't want to say that I'm saying we need RO membranes everywhere, because I do think there are situations where you can do potable reuse without membranes. But membranes do have some advantages for contaminants such as PFAS. And I am going ahead and submitting my survey. So I think there are a lot of chemistry questions that need to be answered. And I might even have a student who's watching this who's working on those chemistry questions. We dabbled in them with, for example, boron, trying to show, a lot of people think if you're blending wastewater with seawater, oh, you're contaminating the seawater. And others think if you're blending seawater with wastewater, oh, you're contaminating the wastewater. But so definitely we need to be looking at the chemical species, the oxidation processes that we do, the disinfection processes that we do in these blended streams.
Great. Well, that is all the time we have. I know there's more questions that I'm sure people would love to continue to engage with you. We really appreciate you coming on and sharing this great information with us today. Just a few really quick things and wrap up for us. The next Third Coast Water Seminar is coming up in February 23rd, and we'll be hearing from Dr. Charles Worth of the University of Texas at Austin, more on drinking water quality. And then, of course, we always would love for everyone to stay in touch with Current. We have a YouTube channel, Twitter, and LinkedIn posts that help us get the word out about events. That QR code on screen is for our upcoming Eventbrite page. Check out our Blue EDU resources if you're interested in water education. We have a curriculum rolled out for our 9th through 12th grade students that's fairly new, so want to share that with our Third Coast audience. But also stay tuned for Chicago Water Week next fall. We're already looking for partners to think about engaging with us for that week-long event anchored here in Chicago. And just generally follow us to stay in touch. We are really excited about the kinds of partnerships and the innovations, like you've heard from Dr. Childress today, that they can enable and drive. And while a lot of the future that you articulated and the research you're looking into might be a way off in terms of large-scale implementation, that's the direction we need to go. So appreciate the push, and everyone have a wonderful rest of the afternoon. We hope to see you on future Third Coast Water seminars. Get in touch with us, stay warm, stay safe. Take care, everyone.